In this video, we will dive deep into how Google File System works. Technology is moving at warp speed. Quantum computers are making headlines, AI is part of our daily lives, and data, it's coming from every imaginable source. With all this cutting-edge tech, you might be thinking, why should we care about a file system that Google introduced back in 2003? Isn't that ancient history in the tech world? In my opinion, Google File System is anything but outdated. In fact, understanding GFS is like finding the blueprint for many of today's big data technologies. It's the pioneer that inspired systems like Hadoop's HDFS and has influenced countless others in the realm of distributed storage. In this deep dive, we're going to unravel how GFS works, why it was such a groundbreaking innovation, and what timeless lessons it holds for us today. We will break down complex concepts into everyday language, so whether you're a seasoned developer dealing with massive datasets or just a tech enthusiast curious about infrastructure behind the scenes, there's something here for you. Ready to jump in? Let's dive deep into the world of GFS. A standard file system, like the one in Unix, is designed for handling modest amounts of data with relatively simple access patterns. It works well for individual machines or small networks where files are typically measured in megabytes or gigabytes. However, if we attempt to use such a file system for managing Google's vast data, such as enormous logs and extensive web content, we quickly run into problems. Standard file systems struggle with the sheer scale, high throughput, and fault tolerance required for processing petabytes of data across thousands of machines. They are not equipped to handle frequent hardware failures or the massive parallelism needed for Google's operations. Recognizing these limitations, Google developed the Google File System, or GFS. While GFS shares common goals with traditional file systems, like performance, scalability, reliability, and availability, it diverges significantly in design to meet Google-specific workloads and technological environment. Let's look at a couple of key observations and design choices. The first observation is component failures are frequent. In an environment with hundreds or thousands of commodity hardware machines, which are affordable, commonly available computers like those we might have at home, component failures are common rather than exceptional. GFS incorporates constant monitoring, error handling, and automatic recovery as integral features to handle hardware and software failures, human errors, and other issues. The second observation is that file sizes are huge. Multi-gigabyte files are standard, often containing many smaller application objects like web documents. On the other hand, managing billions of small files is impractical, so GFS revisits assumptions like I/O operations and block sizes to optimize for large files. While small files are supported, GFS is not optimized for them. The third observation is that write patterns are focused on appending. Files are typically modified by appending new data rather than overwriting existing content. Random writes, like in the middle of the file, are almost non-existent. Once written, the files are only read and often only sequentially. For example, logs of web searches may result in hundreds of thousands of appends per second. You can imagine this being a norm at Google scale. At the time of publishing the paper, Google had multiple GFS clusters deployed for different purposes. The largest one had over thousands of nodes, over 300 terabytes of disk storage, and it was continuously accessed by hundreds of clients. With these requirements in mind, let's look at how GFS works. A GFS cluster consists of a single master node and multiple chunk servers, which can be accessed by multiple clients. Each machine in the GFS cluster is a commodity Linux box running a user-level server process, and it's possible to run both client and chunk server on the same machine. There is also a shadow master that comes into play when the real master fails. We will talk about this later. Let's compare GFS with a standard Unix file system. In a standard Unix file system, data is stored in small data blocks, typically ranging from 4 to 16 kilobytes. The file system uses an allocation map, also known as a free space bitmap, to keep track of free and used blocks on a disk. There are also inodes which store metadata about files, such as permissions, timestamps, and pointers to data blocks. There is also a directory structure which organizes files hierarchically, allowing users to navigate the file system. When you save a file, The file system breaks the file's data into the fixed-size data blocks and stores them on the disk, keeping track of which blocks belong to which file through the inodes. In contrast, GFS uses a central master server that effectively replaces several components of the standard file system. The GFS master keeps track of free and used space across all chunk servers, managing storage allocation at a much larger scale. This is the role of a location map in the standard file system. Similarly, it also has a role of inodes, which holds metadata about files, including which chunks constitute a file and where these chunks are located across multiple chunk servers. And finally, the GFS master manages the global namespace, organizing files hierarchically in a similar directory structure to Unix. Instead of storing data in small blocks on a single disk, GFS stores data in large chunks replicated across multiple chunk servers to enhance reliability and throughput. This design optimizes for large-scale data processing and minimizes the amount of metadata the master needs to manage. This addresses the challenges of handling very large files and datasets common in Google's operations. Now let's see how GFS organizes files in chunks. Files are divided into fixed-size chunks. Google has chosen 64 megabytes, and we'll see why soon. Each chunk has a 64-bit immutable and globally unique ID. These IDs are called chunk handles, and the master assigns them when the chunk is created. Chunk servers would store these chunks on a local disk as Linux files. For reliability, each chunk is replicated on multiple chunk servers. And by default, Google stores 3 replicas, but users can choose a different replication level for different files. Chunk servers provide an API to read or write chunks data associated with a specific chunk handle. But which chunk server should a client use? This is where the master node comes into play. Master stores metadata about all files and their chunks, as mentioned before. The client asks the master for metadata about the file it wants to read or write, caches this information locally for a short period of time, this is to avoid spamming the master, and then proceeds to read or write data directly to and from chunk servers. It is very important that the data is transferred directly between the client and chunk servers to avoid overloading the master. We will now look at an example for a simple read. Specifically, a client wants to read a chunk from a given file. For example, a client may want to read, let's say, a movie file, and let's say it wants to read data ranging from 70 megabytes to 120 megabytes. The client knows that the chunk size is 64 megabytes, so it calculates the chunk index. Let's say that chunk indexes start from 0, so data ranging from 70 megabytes to 120 megabytes will be in the chunk with index 1. The client requests the chunk handle from the master for file, movie, and chunk index 1, and the master responds with chunk handle, chunk 1, and locations where this chunk handle is stored, which is Chunkserver 1 and Chunkserver 2. The client can then download the data directly from chunk servers without further interaction with the master. The master returns a few replicas and the client would choose one of them, usually the closest one. After that, the client requests data to download from a chunk server, for example, let's say Chunkserver 1, by sending a request containing chunk handle and the byte range. In this case, that would be chunk 2, and byte range in chunk 2 would be from 6 megabytes to 56 megabytes, after which the chunk server sends back the requested chunk data. It's very important to emphasize that this example shows reading data from a single chunk. But what happens if a client wants to read data that spans across multiple chunks, for example, a full file? The client would still request data for each individual chunks, except that it would split this into multiple requests before interacting with master and chunk servers. A good thing is that these details are abstracted away behind the client API or CLI tool, so the end user doesn't have to worry about it. We've seen how reads work, but what about writing? Let's talk about mutations, which are operations that change the contents or metadata of a file, such as write or append operations. Write is an operation that changes data to a specific offset of a file, while append adds data at the end of the file. When mutating data in GFS, we have to ensure that it's mutated on all replicas since each chunk data is stored on multiple chunk servers. If a client wants to mutate part of data that spans across multiple chunks or across a chunk boundary, it breaks it down into multiple smaller operations such that each one fits in a single chunk, similar to reads. We could implement mutations naively as follows. Client asks the master, "Hey, Where should I store these data? Master replies, store it on chunk servers A, B, and C. Client then sends the data separately to chunk server A, then to B, and then to C. However, this has two big problems. The first problem is client bottleneck. What do we mean by that? The client has to send the same data multiple times, once to each chunk server. Some of these servers may also be geographically far away, and most likely the data would be transferred sequentially, which would increase the overall latency. Instead, to avoid network bottlenecks and high latency links as much as possible, each machine in GFS forwards the data to its closest machine in the network topology that has not received it yet. Suppose the client is sending data to chunk servers S1 through S4. The client sends the data to the closest chunk server, let's say S1, which forwards it to its closest chunk server of the remaining three, say S2. Similarly, S2 forwards it to S3 or S4, whichever is the closer one, and so on. The second problem is mutation order consistency. For instance, what happens if two GFS clients want to write or append to the same file? The order in which the appended data is added is not important as long as all replicas agree on it. If each client naively writes to each chunk server, there may be race conditions that result in some chunks storing appends in a different order. As a result, chunk data for the same handle may be different among chunk servers, and that would be bad. Let's see an example. Client A appends blue data to some file, and that chunk is located on chunk servers A and B. At the same time, Client B wants to write red data that will be in the same chunk. For example, they both try to append a log line. Chunk server A might process blue and then red, while chunk server B might process them in the opposite order, red followed by blue. This would be very common, especially when the distances between chunk servers and clients are not the same. The final state of the chunk data on chunk servers A and B would be different. So, how does GFS solve this? The idea is to have one primary chunk server that is responsible for choosing the order in which mutations are applied. All replicas must apply mutations in the same order, regardless of which mutation was received first. The client tells the primary chunk server that it wants to mutate some data. The chunk server assigns a serial number to the mutation and then informs other chunk servers. One important fact is that data transfer is entirely decoupled from control messages that assign numbers to chunks, which means that the client can send the data to the closest chunk server while at the same time exchanging control messages with the primary chunk server. Upon receiving mutation data, the chunk server stores it in its LRU cache, which is an in-memory data structure. It keeps it in memory until all prior mutations, based on their serial number, have been persisted. Chunk server clears the data from the cache when it's persisted on the disk or when it's been there for too long, in which case the overall mutation request will fail and the client has to retry. But how do we know which chunk server is primary? We will talk about this in a second. For now, you should know that the GFS master chooses the primary chunk server and the client can get this information by asking the master. Let's see an example of writing some data to a chunk. In the first step, a client asks the master for the location of chunk servers. Then the master sends back locations of chunk servers and tells the client which is the primary one. The other ones are called secondary or replicas. Client can cache this information for some, usually short period of time, and may need to ask server only if the primary chunk server responds that it's not a primary one anymore. The third step is sending mutation data to all chunk servers. This can be done in any order. What happens in practice is the client sends data to the closest chunk server, which happens to be secondary S1. Note that it doesn't have to send data to the primary chunk server because chunk servers will repeat this process until data is transferred to all of them. Decoupling of control messages and data transfers improves performance because we can schedule expensive data transfers based on the network topology. The next step is chunk servers reply when the data transfer is complete. Each chunk server waits for the closest chunk server to acknowledge the data transfer before sending the reply back. This ensures that at the end of this step, the client can assume that all chunk servers have received the data. Once all chunk servers have received the data, the client sends a mutation request to the primary. The request identifies the data that was pushed to all replicas in steps 3 and 4, and the primary chunk server assigns a serial number to the mutation and stores it in its local file system. The primary chunk server will forward this request to all secondary replicas, and each one of them applies the mutation in the same order as the primary one. Note that serial numbers are always incremented by 1, which makes it easy for replicas to know which mutation to apply next. The replicas respond back to the primary, indicating that they have completed the operation. And finally, the primary replies back to the client. If there were any errors at any stage of this process, these errors are forwarded back to the client immediately. For example, depending on when the error happened, the operation may have partially succeeded or not at all. For instance, if the error failed before step 5, then no data was persisted, so the current state is still consistent because the primary wouldn't have assigned a serial number to the operation. But how would clients deal with failures? They deal with it by retrying any failures at or after step 5. It's worth mentioning that consistent write mutations only work within a single chunk, and this is why writes are not used much in practice. Apart from writes, the most common mutation is appending data to the end of the file, such as logs. GFS clients are able to append data to the end of the file even when there are other concurrent appends. The logic that we've just described for writes also applies to appends. For example, if multiple clients want to append data to some file, they can find the last chunk and send the append request to the primary chunk server. If there is enough space in the last chunk, the appends will succeed and will be done in the same order across all replicas. The only bit of extra logic is to handle the case when appending data to the current chunk would exceed the maximum chunk size, which is 64 megabytes. In this case, primary pads the chunk to the maximum size, for example with null bytes, and tells all replicas to do the same. After that, it tells the client to retry the operation on the next chunk. Record appends are restricted to at most 1/4 of the maximum chunk size to keep the worst-case fragmentation at the acceptable level. Also, smaller appends are more likely to succeed without retrying. If the append fails on any of the replicas, the client will have to retry. Unfortunately, this may result in the same record being written twice. Intermediate failures could still be retried to minimize the chance for duplicate records, but the GFS doesn't guarantee that the bytes in each replica are completely identical, only that each unit is written atomically. It's up to applications to deal with this, and in practice, this is often not difficult since the exact same data or already processed data can be tracked. This raises an important topic for discussion, which is consistency guarantees. Consistency models are a complicated topic in distributed systems. GFS has a relaxed consistency model. What does this mean? If mutation operations succeed, then the data is consistent, which means that all clients will always see the same data, regardless of which chunk server they read from. When writes to a file succeed without any failures and there were no concurrent writes, the state of the file is consistent and all the clients will see what was written in its entirety, even when writes span across chunks, since there is only one writer. However, if multiple clients write data that spans across multiple chunks, it may happen that the state of the file is consistent, but it may not reflect what any single write intended to do. When the state is consistent and all clients see what was written in its entirety, the state is said to be defined. We say it's undefined but consistent if all clients see the same data, but concurrent writes may be interleaved. Let's take a step back to talk about chunk server leases. Leases are a common concept in distributed systems that have an expiration time. We've said that the master chooses the primary chunk server, but we didn't say exactly how that works. Each chunk is distributed across multiple chunk servers, and at most one is primary at any moment. Note that other chunks in the same file may have different primary chunk server. The way this works is the master grants a chunk list to one of the chunk servers, for example by sending a message to the chunk server, and that chunk server is called primary. They are designed to minimize the management overhead on the master. As long as the lease is valid, the chunk server is the primary. A lease has an initial timeout of 60 seconds. However, if the chunk is being mutated, the primary can request and receive an extension from the master indefinitely. The master may sometimes try to revoke the lease before its expiration time, for instance to disable mutations on a file if it wants to. It is very important to ensure that only one active lease exists at all times to avoid multiple chunk servers making mutation order choices. Even if the master loses communication with the primary, it can safely grant a new lease to another replica after the old one expires. There is one more important thing that we didn't talk about, which is master metadata. We've said that the master stores some kind of data about chunk servers and locations, but we never really dug into it. We'll do that now. The master stores three major types of metadata. These are file path for files and a chunk handle for chunks. It also stores the mapping from files to chunks, as well as the locations of each chunk's chunk server. But how is this data persisted? What if master crashes? Master persists the first two types of metadata by logging mutations to an operation log, which is a file that is stored on a disk and replicated on some remote machines because it's very important and cannot be lost. This operation log file makes it easy to update master state without worrying about inconsistencies when the master crashes. If that happens, the master can read the operation log line by line and recompute the final state. When the operation log becomes too big, the master can take a snapshot so he doesn't have to replay the full thing each time. The third type of metadata, which is chunks locations, is not persisted on the master. Instead, these are stored in memory. If the master crashes, it queries all chunk servers in the cluster to recompute the state. It can also keep its state up to date by periodically querying each chunk server with regular heartbeat messages. Another way to look at this design decision is to realize that a chunk server has the final say over what chunks it does or does not have on its own disk. One of the main benefits of using GFS is that it provides resilience to hardware failures. So, what happens when a chunk server fails? How does GFS ensure that data from failed chunk servers is replicated? The master uses a heartbeating mechanism to detect chunk server failures. Each chunk server sends periodic heartbeat messages to indicate it is functioning properly. If the master doesn't receive a heartbeat from a chunk server within a reasonable time frame, say 1 minute, it assumes that the chunk server has failed. Since the master stores all metadata in memory, including the locations of chunks and their replication states, it can quickly and efficiently scan through its entire state. This allows the master to identify any chunks that have fallen below the desired replication factor due to the chunk server failure. The master then instructs other chunk servers to replicate these lost chunk replicas. It selects the best candidates for replication based on factors like current workload and network topology to optimize performance and balance the load across the system. By proactively detecting failures and managing chunk replication, GFS ensures that the data remains highly available and reliable, even in an environment where hardware failures are common. This design allows GFS to maintain the desired level of data redundancy and to continue serving client requests without interruption. We've seen how GFS handles chunk server failures, but how does it deal with master failures given that there is a single master? A new master can be started quickly by processing the operation log to recover its state. Chunk servers and clients use a DNS alias for a master such as GFS test or GFS prod to connect to it, which can easily be changed if a new master needs to take its place. Instead of just starting a new master server upon failure, there are shadow master instances that maintain a read-only access to the cluster and can be promoted if the primary one fails, without having to even load any state from disk. There is a lot more to talk about when it comes to Google File System. We haven't discussed garbage collection, high availability, directory structure, etc. However, we have covered a lot and it should give you a good grasp on how GFS works, and hopefully you can make a reasonable guess by now how some of these things would be implemented. Google doesn't use GFS today because a single master has reached its limits for the amount of data Google deals with. However, HDFS, which is based on GFS, is still used today. If you've enjoyed this video, please hit the like button, subscribe, and share this video with your friends, and let me know if you'd like to see more videos of this kind. See you in the next one!